Still talking about transformations. We're now going to look at vertical stretch / compression. So in looking at vertical stretch and compressions, we're going to use the function, the absolute value of x. And so you'll see the absolute value function graphed here, and you'll see a table. Absolute value means what is the distance from 0. -4 is 4 steps from 0. -3 is 3 steps from 0. -2 is 2 steps. -1 is 1 step. 0 is 0 steps from itself. 1 is 1 step. 2 is 2 steps. 3 is 3 steps. 4 is 4 steps, and so on. Now, in this transformation, we are going to stretch this function vertically by multiplying it by 2. So it's 2 times the absolute value of x. Now what this does is it takes our, let me make that a little bit straighter, it takes our outputs as they were and literally just makes them 2 times bigger, 2 times the absolute value of x. So we have the absolute value of x, and we're just going to make them all twice as big as they previously were. Now, twice as big, 0 twice as big as it was, is still just 0. But what you're going to notice is that when we graph this, it is going to get pulled upwards. Every point and the corresponding point is going to be twice as tall as it was before. Now what I mean by that is this. So if we look at these points, that's the point 1, 1. It is now the point 1, 2. It was 1, 1, now it's 1, 2. It was the point 2, 2 right there, but now it's the point 2, 4. It's twice as big as it was. And functionally what happens is it's almost like somebody grabbed these endpoints here and pulled them upwards, stretched them upwards all the way until that line was pulled up to this angle. So when we looked at shifts, the shape of the graph was maintained, but it moved around. When we looked at reflections, the shape of the graph was maintained, but it was reflected across an axis of symmetry. This is the first time we are looking at a shape that is literally changing. The angles on this are changing. Now, a vertical stretch. Now, what would happen then if we had said f of x is 3 times the absolute value of x? Well, hopefully, intuitively, we would just make another column and make all of the output values 3 times what they originally were, or 4 times what they originally were, 5 times, or 6 times. We can stretch this vertically as much as we want. Now, please note that this is vertical stretch and compression. When we're talking about stretch, we're stretching it upwards. This right here, often referred to as a, that multiplier, or multiplying by, to be a vertical stretch, a has to be greater than 1. So when a is 1, that is just 1 times the absolute value of x, which is just the absolute value of x. That's the original. Anytime it gets bigger than 1, though, it's going to be some multiplier larger. It's going to be stretched up. So if a stretch means a is greater than 1, then hopefully it's intuitive to you that compression is when a is between 0 and 1. So we're using kind of a set builder notation there, between 0 and 1, as in fractional values. So if I were to write f of x equals 1/2 the absolute value of x, what that means is that all of my outputs are now 1/2 the size they originally were. 1/2 the size they originally were. So I know what my original outputs were, but they're going to be half as big. So the original absolute value of -4 was 4, but it's now going to be half that size. It's going to be 2. Originally it was absolute value of negative 3 was 3. Now it's going to be 3 halves. 2 becomes 1, and then 1 becomes 1 half. Half of 0 is still 0. But what you'll notice in this symmetry is that it flattens out this curve. It compresses this curve. So that was 1 half, and that was 1. That was 1.5, and that was 2. And this curve, or not this curve, but this line, which had a slope of 1. Each of those had a slope of 1, and then I guess negative 1 coming down. But it's literally like someone grabbed hold of these originals and pushed them down, flattened them out, or compressed them. And so we have the ability to pull up, vertically stretch by multiplying by an a value, a multiplier that's greater than 1. But we can also compress or flatten out a graph by multiplying it by a fractional value, something between 0 and 1. So we can change the shape, either stretching it up or stretching it down, as well as all the other ones. And so when we talk about absolute value, so the parent function is this, but I want to include this important piece of information. We've done all of these different transformations, but they can all still be used together. And so the last thing I want to say in this video is this: if we bring together all of what we know, we can do this. All of these different things. So just to label these real quick, this was our reflection over the x-axis. Oops, I'm going to put that in parentheses. I forgot this one right here. A was our stretch compression. Stretch compression. And I need to note that that is the vertical stretch compression. I'm going to talk about horizontal here in the next video. That one right there is our reflection over the y-axis. We have our horizontal shift. And lastly, we have our vertical shift. All the different things that we can do to this. Shift it up, down, left, right. We can reflect it over the x-axis, reflect it over the y-axis, and we can actually change the shape, stretching and compressing it vertically.